So the question is, a marble with a radius of r is equal to 1.0 centimeters and the mass of m equals 5.0 grams is released from rest at a height of h equals 0.60 meters on a plane inclined at theta is equal to 45 degrees. It rolls down the plane and along a horizontal table. The table is h equals 1.2 meters above the ground. How far from the edge of the table does the ball land? Okay, so to answer this question, once the ball leaves the edge of the table, it's going to travel with projectile motion to the ground like this. So it's going to follow some parabolic path. So in order to work out this range here, we're going to need two things. We're going to need the initial speed as it leaves the table. We know that's horizontal because it's a horizontal table, and we'll also need the time to ground. So let's start by working out the initial speed. To get the initial speed, we can consider the energy conversions which take place as the marble is released from rest here. So if we assume mechanical energy is conserved, okay, which is reasonable because this holds when non-conservative forces don't do any work. In this case, we do have friction between the ball and the plane. That's what makes it actually roll rather than just slide. But because the surface of the ball is not moving against the plane, it's stationary at the point where they touch, that friction isn't actually doing any work. So this is a reasonable approximation. So we've got that the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy. Now in this case we are told that it's released from rest. So that tells us that the initial kinetic energy is 0. We'll also consider the final potential energy to be 0. So we'll look at the change in potential energy between this point and this point, setting this one here to 0. Okay, so the initial potential energy, that's all in the form of gravitational potential energy. So that's given by mgh. Now this final point, this is what it has at the bottom of the slope. So at the bottom of the slope, it's got two types of kinetic energy. It's got the rotational, plus it's also got translational. So we've got a half I omega squared, and then we've also got a half mv squared. Okay, now it is a sphere because it's a marble. So we have that I for a sphere is equal to 2/5 mr squared. And we've also got our equation v equals omega r. So we can rearrange this to write omega is equal to v over r. So what we're going to do is substitute these in here now. So this is equal to a half times I, which is 2/5 mr squared, times omega squared, which is v squared over r squared. And then we've still got the plus a half mv squared. Okay, so we've got a 2 on the bottom and a 2 on the top. We've also got an r squared on the top and an r squared on the bottom, which can cancel. So we can write this as a 5th mv squared plus a half mv squared. Now these both have mv squared, so we can write this as mv squared times a 5th plus a half. And then to add these two together, we want to give them a common denominator, so we'll write it as over 10. This is 2 plus 5, so this is equal to 7 over 10 mv squared. Okay, so now you can see we've got mgh is equal to 7 over 10 mv squared. We've got an m on both sides, so we can cancel that out, and we end up with gh is equal to 7 over 10 v squared, which we can rearrange to find v, because that's what we're trying to find, the speed as it leaves the table, which is the same as the speed at the bottom of the incline here. So we've got v squared is equal to 10 over 7 GH, which tells us that V is equal to the square root of 10 over 7 GH, and we can actually evaluate this. So we've got 10 over 7 times 9.8 times h, the height, which we were told was 0.60, and solving that, we end up with 2.90 meters per second. Okay, so now we've got the initial speed. Now what we need to do is calculate the time to ground. So to do that, we're going to use our kinematic equation. We can use S is equal to UT plus a half AT squared. We're going to look at the vertical direction to get the time. So this will be SY UY AY T squared. Now, vertically, it has no initial speed. Initially, because the table's horizontally, it's traveling in the horizontal direction. So this time here is 0. So we can write this equation as h, so that's the height to the ground, it ends up lower than it starts, is equal to a half times g times t squared. So g here is acting downwards, so the change in height and g are in the same direction, so we don't have a negative sign here. So we can rearrange this to get t, so t is equal to 2h on g, and we take the square root of that. And we can evaluate this as well, so we've got 2 times 1.2 over 9.8. Solving that on the calculator, we end up with 0.495 seconds. Okay, so now we know how fast it's traveling horizontally, and we know how long it takes to get to the ground. So just using the horizontal form of this kinematic equation, here we know that the range, the distance traveled, is equal to ux times t, and there is no acceleration in the horizontal direction. So this speed in the x direction is the 2.90, the t is the 0.495, and solving that, we end up with 1.4 meters. So that's the answer to this problem. You may have noticed that there was quite a lot of information given in this question that we didn't actually need to use. So we didn't need to know this radius for the marble. We didn't need to know the mass of the marble. We also didn't need to know how much the plane was inclined. It would be possible to answer this question by considering forces as well and working out the acceleration, but for questions like this, the energy approach is actually an easier approach to use.